Good morning, everyone. Today, I would like to explain the Unit 3 summary as well as generator load models and numerical problems in Unit 3 of PSOC, Power System Operation and Control. This might be video number 20. Now, let me explain generator load model. In the previous class, you understood that the governor model, and previous classes you understood that turbine models. Now, let me close the LFC loop. For that, generator load model is quite essential, in which generator means synchronous generator. Generally, generator from rest to its rated speed position, generator runs from 0 to rated speed, ns synchronous speed, in which the kinetic energy is stored in the form of rotating parts. The kinetic energy is proportional to square of the speed or square of the frequency, and hence the kinetic energy at rated speed is proportional to f naught square. F naught is the rated frequency or nominal frequency. Kinetic energy Wke is proportional to f square. This is Wke naught proportional to f naught square. Therefore, the proportionality constant may be k, and hence Wke equal to k into f square, and Wke naught equal to k into f naught square. Now divide both of them, Wke naught, you will get k get cancelled. So f Wke by Wke naught equal to f by f naught whole square. So therefore, in the next line, in the next equation, you will get Wke equal to Wke naught, the kinetic energy stored at rated frequency or rated speed, into f by f naught whole square. F is the frequency at a particular load, f naught is the no load frequency or rated frequency. That is equal to, the unit is megawatt seconds. And the damping term D is defined as dou PD by dou F, megawatts per hertz. The unit is megawatts per hertz. Therefore, delta PT, change in turbine power, equal to delta PD, the change in power demand, plus dWke by dt, the change in kinetic energy in the rotating parts, plus damping term d into delta f. In general, d into delta omega is used. Here you can multiply with 2 pi, so that 2 pi is combined with d. For understanding purpose, I included that. Otherwise, you can also use some other term b here instead of d. For remembrance, d is used here. Therefore, d into delta f. So therefore, f is equal to f naught plus or minus delta f. F naught is the nominal frequency or rated frequency. Delta f is the change in frequency due to variation in the load. It may be plus or minus based on type of load increment or decrement. Therefore, in the generator load model in the second slide, Wke equal to Wke naught into f by f naught whole square megawatt second. The unit is megawatt second. Now, this Wke naught into f naught, f is equal to f naught plus delta f. In fact, you can use plus or minus here, divided by f naught. whole square. So here this term can be divided into or approximated as 1 plus 2 delta f by f naught plus delta f by f naught whole square. This and second and third terms can be approximated as wke naught into 1 plus 2 into delta f by f naught. Delta f is the change in frequency due to change in load. F naught is the initial frequency or rated frequency. So, and hence delta pt minus delta pd equal to 2 into wke naught by f naught into d by dt delta f plus d into delta f megawatts. D into delta f megawatts. This is the equation. So this term is related to kinetic energy, change in kinetic energy of the machine, and this term is related to damping factor of the load. Now generator load model continuation, third slide, delta PT minus delta PD. So PT is the turbine output, PD is the power demand. So that is equal to kinetic energy term as well as damping term. Now by simplifying 2 naught by f naught equal to 2h by f naught. H is the inertia constant. In general, typical value of the h is 2.8 seconds. In general, m is equal to 2h or Tm is equal to 2h. Tm is the mechanical time required to start the machine from rest to rated speed. So that is the time required to start the machine. That time is 2.8 into 2, approximately 5.6 seconds. So that is the time required for starting the machine towards the inertia. That energy is stored in the form of kinetic energy and it will run the machine at rated speed by consuming that much energy. So therefore, H is inertia constant can be expressed in terms of seconds, 2.8 seconds approximate value, and delta Pt minus delta Pd of S in Laplace domain, that is equal to 2h by f naught into S d by dt equal to S into delta Fs plus d into delta Fs. Therefore, delta F is common equal to Gp of S into delta Pt of S minus delta Pd of S. Therefore, Gp is the transfer function of the generator load model, that is equal to Kp over 1 plus S into Tp, where Tp equal to 2h by f naught into d. Sometimes f, if d is expressed in terms of omega, so this is equal to 2 pi, so 2 get cancelled, h by pi f into d. That is the actual term. Alright. Therefore, this is the transfer function of generator load model. Kp is the gain and Tp is the time constant. In general, Tp is 10 seconds and Kp is 100 around. So that is the typical value of the generator load model. Now, by closing the ALFC loop, primary ALFC loop, you can understand that this is the turbine transfer function, governor transfer function. This is the generator load model, and the output of the generator load model delta F. This is the delta PD is the disturbance or load variation, and here it is delta F is the output. That delta F is taken here and passed through the 1 by R. R is the regulation or droop. So this you will get the negative sign. This is the primary ALFC loop in which speed governing system is acting and controlling the speed according to load variations. And secondary ALFC loop, already I explained you that this delta F is passed through the slow acting integral controller so that you will get the change in the error can be reduced to 0. you can offset the steady state error. So therefore, secondary LFC loop is the slow acting loop, primary LFC loop is the fast acting loop compared to secondary one. So this is with and without controllers. So single area load frequency transfer function model, including governor, turbine as well as generator load models. All right. So typical values of the single area LFC loop, generally R is less than or equal to 5%. This is droop or regulation. Time constant of the turbine TT equal to 0.222 seconds. TR is the reheater time constant around 10 seconds. KR is the reheater gain 1 minus fraction of the reheated steam, and TH is approximately 0.1 seconds. Hydraulic hydraulic amplifier. TG is the governor time constant 0.1 seconds. TP is the power system time constant 20 seconds. KP is approximately 100. So these are the typical values of various components. After that, let me explain the state space model of a classical generator. So here generator is there. So generator is supplying the infinite bus. The classical model is E dash is the generator voltage, X dash is the reactance of the generator, V is the terminal voltage, P equal to V E dash by X dash into sine delta. So delta P equal to dou P by dou delta into delta delta. So that is equal to V E dash by X dash into cos delta into delta delta. Therefore, dou P by dou delta equal to T naught into delta delta. T naught into delta delta. T naught is the synchronizing torque coefficient. So there is the swing. This swing equation is m d square delta by dt square equal to Pa, that is equal to Pm minus Pe minus d into delta omega. Now I have used here d in terms of delta omega. So now let us express d delta omega by dt equal to 1 by 2h into Pm minus Pe minus d delta omega. So that is expressed as 1 by 2h into minus T naught delta delta minus d delta omega plus u. U is the input. Input is Pm. Mechanical input, that is Pm. Here delta omega is equal to x1. X1 dot is equal to d delta omega by dt, and x1 dot is equal to minus d by 2h x1 minus T naught by 2h x2 plus 1 by 2h u. So therefore x2 equal to x2 equal to d delta, x2 dot is equal to omega net into x1. So therefore these two equations are state space equations. You can arrange x1 dot x2 dot is equal to minus d by 2h minus T naught by 2h. First row, second row omega naught and 0, and x1 and x2. There is a error is there, correction, you can change that correction, plus 1 by 2h 0 into u. So this is the state space model of classical generator. Now review of the swing equation. Let us take the generator. The P is the output of generator, and T. So here Pm is input. The Pm is input. Therefore, Te corresponding to Te, T into omega. Pe is equal to T into omega, and Pm is equal to Tm into omega. Omega s. So now let us omega. Omega is rated speed, the particular synchronous speed. The Tm is rotating in the clockwise direction. Te is opposing the Tm. So that opposition is converted into electrical power Pe. So therefore, J, the moment of inertia, J d square theta m by dt square is equal to Tm minus Te. The variation between Tm and Te is converted into electrical power output. So therefore, so this entire equation you can multiply with omega sm, synchronous speed. So that you will get the swing equation m d square delta by dt square equal to Pm minus Pe minus d into delta omega. So d square delta by dt square is equal to d square theta e by dt square, and theta e and theta m both are related. Theta is equal to pair of poles into theta m. That you know that concept. So recall that concept. Finally, h by pi f into d square delta by dt square equal to Pm minus Pe minus d into delta omega. So this is the review of swing equation. All right. Now the dynamic interaction between the PF and QE loops and load frequency and as well as uh, automatic voltage regulator loops. For small deviations, there is a little interaction between the two loops. The dynamic During the dynamic perturbations, there will be a considerable coupling between the two loops. Dou P by dou V, voltage fluctuations leads to load fluctuations. The change in QV loop will change the V, which affects P. Therefore, QV loop is faster than the PF loop, and changes in the QV loop will be completed before the PF loop acts. Therefore, this coupling between these two loops can be neglected because of the due to dynamic interaction. Why? Because the AVR loop is very faster compared to ALFC loop. So therefore, QV and PF loops. Why you can neglect the uh, interrelation between these two loops? So the relation between these two loops can be neglected. Now let us consider the generator E at delta is supplying the power to a bus bar V at 0. The generator reactance is X. The current flowing through the generator to bus is I. So I is equal to E at delta minus V at 0 divided by X. Now E by X delta 90. J means minus 90 here. Minus V by X into minus 90. I conjugate is equal to E by X 90 minus delta minus V by X 90 degrees. So S is equal to VI conjugate. By using that relation, P can be expressed as the X component of this relation. Therefore, VE by X cos of 90 minus delta, that is equal to EV by X sin delta. Cos 90 minus delta equal to sin delta, and hence so frequency delta and omega all are related compared. So therefore, interchangeably you can use these two terms, and hence Q is equal to V by X sin 90 minus delta minus V square by X sin 90, that is equal to V by X sin 90 minus delta delta. So delta Q is a small variation in the Q, so that can be expressed like that, minus V square by X sin 90, which is equal to V by X into E minus V. E minus V is nothing but delta V. So therefore, delta Q and delta V both are strongly related. So delta P and delta delta are strongly related, and hence, so the intercoupling between the P and voltage, Q and frequency or delta can be neglected, and hence the cross coupling between these two control loops can be neglected. So, alright, therefore, cross coupling can be neglected. Now coming to the droop control, here you can adjust the droop upwards and downwards so that wherever you need to have a rated frequency, you can adjust the droop of generator. So here let us consider these two lines. This is the droop. Here at 99% it is having the point, it is 98%. By changing the loop, you can change the variation. For these two adjustments, one is 25% load, the second one is 50% load. So therefore, 50% load can be changed so that 25 to 50% load can be varied with the same frequency or same speed by adjusting the droop of the machine. All right. So it is used to get the proper load division among the running units. So therefore, droop adjustment is very important. So in the subsequent chapters or discussions, we can use this concept for solving the problems. Now, load sharing between two units. There are two units, 1 and 2, are synchronized together to feed the common load PD, and E1 and E2 are the generator voltages, X1 and X2 are the reactance of the parallel units. Here, 1 and 2 droops are drawn here. This is the first generator, this is the second generator, right side and left side respectively. So both are supplying a load of P1 and P2. So PD is equal to P1 plus P2. The corresponding frequency is F1. So when the load is varied from PD to PD dash, then P1 plus P2 dash, the second unit can be adjusted or first unit can be adjusted. Here first unit is adjusted. Therefore, P1 dash plus P2. Like that you can have. And the droop is defined as N naught minus N by N or F naught minus F by F. F naught is the no load frequency, F is the frequency at a particular load. So therefore, R is equal to minus delta F by F, so delta P. So therefore, it is expressed in terms of H per megawatt. So this is the load sharing. You can adjust one among the units so that you can share the load with a constant frequency. Now let us understand numerical problems, solve the numerical problems. So in the load frequency control, the unit 3. So first problem, let us consider a numerical problem. A 125 MVA turbo generator operates on full load. Full load means 125 MVA at 50 Hz. The frequency operation is 50 Hz. When it is full load, the frequency is 50 Hz, rated. At rated load, the droop is adjusted like that. Now, full stop. A load of 50 megawatts is suddenly reduced on the machine. Reduced on the machine. What happens? 50 megawatts is suddenly reduced. If you consider the unity power factor load, 125 MVA means 125 megawatts. Now in the second case, 125 minus 50, 75 megawatts. Okay. The steam valve to the turbine commences to close after 0.5 seconds. Why? Because there is a time lag in the control loop, load frequency control loop, that due to valve openings and closing. So therefore, that time is time lag, that is nothing but 0.5 seconds due to time lag in the governor operation. Full stop. And assuming the inertia to be constant, and that is equal to H is equal to 6.6 6 kilowatt second per kVA. Kilowatt second per kVA. If it is unity power factor per kVA, you can have kilowatt. 6 kilowatt second per kilowatt. Kilowatt get cancelled, you can get 6 seconds of generator capacity. Calculate the change in frequency that occurs in this time. Okay, so that is our question. So initially, first let us understand the problem properly. A generator, the rating is 125 MVA. It is operating at full load, and the frequency at full load is 50 Hz. Now, suddenly the load is decreased by an amount delta PD equal to 50 megawatts. So the steam valves will operate with a time lag of 0.5 seconds. In the meantime, the frequency can be changed, and the inertia constant is given equal to 6. Now let us find out the change in frequency. That is our question. Now let us solve this problem. So this solution, H is equal to stored energy divided by capacity of the machine. Capacity is nothing but the full load rating of the machine. 125. H is 6. So therefore stored energy at no load equal to 6 into 125 into 1000, 750 megajoules. 750 megajoules at no load. So when the frequency is increased, speed is also increased, and the delta F is the change in frequency. The delta F can be represented in the equation F2 is equal to F1 plus delta F. F2 is the new frequency due to change in load. Now the excessive energy input in 0.5 seconds. Energy input in the sense already generator is getting power input PM, and suddenly the load on the machine is decreased. PM cannot stop instantaneously, therefore cannot be decreased instantaneously. It will take some time. PM is decreased with the amount of 50 megawatts. Then it will take the time 0.5 seconds. In the meantime, the change in energy equal to 50 into 0.5 into 1000, 25 megajoules. 25 megajoules is the excess energy. So therefore, F2 equal to square root of the new energy divided by old energy into nominal frequency. Therefore, 750 plus 25 is the total energy at this instant divided by 750 is the initial energy at rated speed. Therefore, the frequency is 50 into 50. You'll get 50.83 hertz. Load on the machine is decreased when you are operating at full load and rated frequency. Again, the frequency will increase as you are not adjusting the droop, so that the change in frequency is there, 50.83 hertz. If you adjust the droop so that you will get the 50 hertz, in that case the droop characteristic can be adjusted so that you will get the same frequency here also. That is our question. Let us understand the question properly and then solve the problem. 125 MVA generator is operating at 50 hertz at full load. Therefore, when the load decreases, naturally speed increases, frequency also increases. So this is question number 1, problem number 1. This is very important. So they can twist you. So they will twist the question in the examinations. So that read properly and practice more problems. Now coming to the second question. Problem number 2. There are two generating stations. Here generating station with rating 200 megawatts, generating station 2 the 100 megawatts. The loads are at station number 1. This is 75. You can change this value, 75 megawatts. This is 25 megawatts. And station number 1 and 2 are connected with a transmission line of reactance X via a MG set, synchronous generator and indexed motor set is connected. Now let X be the megawatts. X megawatts are flowing from station 1 to station 2. Station 1 to station 2. So when this power is flowing, then what happens? The station 1 load is 75 is here. Instead of 25, you write 75 here. 75 plus X. is the total load on the station 1. Therefore, the drop in the speed is nothing but 75 plus x divided by 200 into 4. Into 4 in the sense, from no load to full load, the change in speed is 4%. That means from 0 to 200, it is 4%. From 0 to 75 plus x, it is 75 plus x divided by 200 into 4. Understand? Similarly, total load on the station 2 is 50 minus x. So x is flowing from 1 to 2. Therefore, 50 minus x. Here you can write here 50 megawatts. Here it is not 25, it is 75, it is 50. 50 minus x. Percentage drop in the speed at station 2 equal to the full load variation is 3.5%. From 0 to 100, variation is 3.5. Therefore, now the load is 50 minus x. Therefore, 50 minus x divided by 100 into 3.5. That is the load. Therefore, load on the mg set, this is the second equation. Third equation, load on the mg set is x megawatts. Since x megawatts is flowing from here to here, in between this mg set is there, and hence it is x. Therefore, full load variation is from 0 to 25, the variation is 2.5. When x megawatts are there, x by 25 into 2.5, that is the drop in speed at mg set. Therefore, mg set and station 1 both are connected directly, and this is nothing but one control area. This is second control area. In between, the transmission line is there. This is the reactance. So, and hence, the sum of drops in speeds in station 1 is 4 by 200 into 25 plus x plus 2.5 x by 25 equal to 3.100 into 50 minus x. Therefore, by solving this equation, x is equal to 1.67 megawatts. You will get x is equal to 1.67 megawatts. Therefore, load on the station 1, 75 plus x, therefore 76.67 megawatts. Load on the station 2 equal to 50 minus 1.67, therefore 48.33 megawatts. The load on the mg set is 1.67 megawatts. So, therefore, let us understand once again problem number 2. Here, this station 1, station 2 both are connected with a transmission line and mg set. The mg set is connected at the station 1. In between station 1 and station 2, some transmission line is there. That transmission line offers some reactance x. Therefore, this is one control area. The second control area is station 2 alone. Station 2 alone. The load on the station 1 is 75 megawatts. The load on the station 2 is 50 megawatts. You note down that point. Here 25 megawatts have been shown, but you change that value. Let x megawatts is flowing from station 1 to station 2, so that the load variation, the load on the station 1 is 75 plus x, the corresponding variation is here 4 by 200 into 75 plus x. Similarly, load on the station 2 is 50 minus x, therefore 3.5 by 100 into 50 minus x. The load on the mg set is 2.5. 2.5 by 25 into x. So now the station 1 as well as mg set, the summation of these two drops equal to drop in the station 2 control area. Control area 1, control area 2. See. Therefore, after solving that, x is equal to 1.67 megawatts, that is load on the mg set. Load on the station 1, 76.67. And similarly, load on the 2 is 48.33 megawatts. So that is problem number 2. Problem number 3, two generators rated 200 megawatts and 400 megawatts are operating in parallel. and droop characteristics of their governors are 4% and 5% respectively from no load to full load. Full stop. Assuming that the governors are operating at 50 Hz at no load, please remember here 50 Hz frequency at no load. Previous problem, this problem, both are different. How would a load of 600 megawatts be shared between them? If the load on total system is 600 megawatts, then what is the load sharing between these two units? What will be the system frequency at this load? And find out the frequency f. F naught is given 50 Hz. Assume free governor operation. Instantaneously governor is operating. There is no time lag here. And repeat the problem if both the governors have the same group, that is 4% instead of 4 and 5. So this is the question number 3. Now let us solve this problem. Let load on the generator 1 is x megawatts. We don't know what is the load on the generator 1. So therefore let it be x megawatts. And load on the second generator is total load is 600 PD. So 600 minus x is the load on the generator 2. Okay. Now you understood the loads on each of the station generators, x megawatts and 600 minus x megawatts respectively. Now the change in frequency is delta f. Change in frequency is delta f. Change in frequency is expressed in terms of generator 1 and generator 2. So generator 1 load is x megawatts. The rating is 200. And the droop is 4%. F is the, so let us have this is F. F is equal to rated to here. Therefore, load is x by 200 into 4%, 0.04 into frequency is 50 Hz. Therefore, it is equal to 0.04 x by 200 into 50. That means at 200, variation is 0.04. At x, what is the variation? X, what is the variation? X by 200 into 0.04. That is the variation into rated frequency 50. Similarly, for generator 2, total load is 600 minus x. Rated value 400. Therefore, 600 minus x by 400 into 5% droop. Therefore, 0.05. Directly, I am writing here 0.05. Therefore, this is equal to 0.05 by 400 into 600 minus x into 50. So, both are same. So, here 600 minus x by 400 into 0.05. That is the delta f. So, this delta f both are same because both are connected in parallel. And hence, both you can equate both the equations so that only unknown is x. Find out x from the equation, you will get 231 megawatts is the x value. That is load on the generator 1 is 231. Now let us find out the load on generator 2. The total load is 600. 600 minus x, 369 megawatts. 369 megawatts. Use one of the equations to find out the delta f. So by using that, you can get delta f is equal to 0.04 by 200 into x. X is 231 into 50. That is equal to 2.31 Hz. 2.31 Hz. Now the frequency is equal to f naught minus delta f. That is equal to 50 minus 2.31. That is equal to 47.67 Hz. That is the frequency due to load variation. Frequency variation due to load variation. So that is delta f. That is solution for the First part. Second part, repeat the problem if both the governors have the group of 4% only. So when the equal groups are there, then the load can be shared proportional to their ratings. Proportional to their ratings. Now let us use the x here. In the second equation also, this is equal to 0.04. So 0.04, 0.04. Let us equate them. You'll get the x is equal to 200 megawatts and 600 minus x is equal to 400 megawatts. So both are sharing the load as per the rating, and the frequency will be, so delta f will be 2 hertz only, and f is equal to 48 hertz. That is the variation when they have equal groups. The frequency can be increased compared to previous case. Therefore, the synchronization of the generators with equal groups is better choice than unequal groups. So 4% group for both the generators. Pg1 is equal to 200, Pg2 is equal to, Pg1 is equal to 200, Pg2 equal to 400. Okay. And delta F is equal to 2 hertz, and system frequency F is equal to 50 minus 2, 48 hertz. This is the solution of problem number 3. Now the problem number 4. Let us solve this problem. A 100 MVA synchronous generator operates 100 MVA is the full machine operate. The load only reduced to 50 megawatts. 50 megawatts, 100 to 50. Due to time lag in the governor system, the system valve begins to close after 0.4 seconds. It is similar to that of the first problem, but numericals have been changed. Determine the change in frequency that occurs in this time. I'm sorry. Determine the change in frequency that occurs in this time given h is equal to 5 kilowatt second per kVA of generator capacity. Similar problem we have solved. The K is stored equal to 5 into 100 into 1000, 5 into 10 power 5 kilowatt second, kilojoules. Excess power input equal to 50 megawatts for the time period of 0.4 seconds. Therefore, excess energy is 50 into 1000 into 0.4, 20,000 kilowatt second or kilojoules. And the frequency at the end of 0.4 seconds, already you know that 50 into square root of WKE plus delta WKE divided by WKE. So 50, 5 lakhs plus 20,000 divided by 5 lakhs. Here you can use one more 0. You will get the 51 hertz. 51 hertz. I'm stopping here and thank you.